science fiction. We make no guarantees, however, how long it will remain fiction. Fiction. Fiction.
Spacious salutations, cognonauts. My name is Ayla, and this is ExoFathom. Today we're doing a little exo bit, and this is on all levels a show where we basically sit around and ponder the mysteries of the universe. And of course, as always, I'm joined by my two lovely co-hosts, Nick and Mike. Nick, how are you doing tonight?
Wonderful.
Good.
Yeah.
Good. Okay, great. Mike, you?
Hanging in there. You know,
Nice. All right. Same as usual.
how are you doing?
Well, I have to say, I am a little bit nervous, and I think it's kind of silly because I'm like, yeah, this is probably being broadcast live to like one person. So to that one person, thank you for listening. I will try to not talk so fast. But I'm a little nervous because I bit off more than I could chew with tonight's episode, which is on the Hubble Constant. And it's going to be
Story of our lives.
Yeah.
You should. It's good. It's how you
Yeah.
progress.
I think so. I think I just really bit off more than I could chew in what's designed to be a 30-minute to 45-minute exobit. But so we'll see how far we get, and we might want to continue this into another episode. But basically, I found an article with innovations in the measurement of space and time, and it was a complete rabbit hole. And so just to start, and to just slow me down a little bit, I wanted to just share a quote. And it's good old Einstein, and it reads, "Time is what prevents everything from happening at once." And I really liked it for this episode because in a lot of ways, it does allude to the Big Bang and how we were this dense ball of energy and matter. And then this Big Bang happens and the clock starts, and that's what we know to be the beginning of time, at least as I would understand it for this show. But how about the two of you? How do you define time, and how do you think of time?
Well, I mean, partly a construct, partly a measurement of heavenly bodies moving. I don't know. I mean, to me, I don't even know if time really exists outside of our just own perceptions. So
I agree. It's part of why I'm so nervous with this episode. There's a lot to say about time. Mike, how about you?
I have a pretty strong hate relationship with time. I don't like to think that it exists. And,
Okay.
yeah, which can cause some problems, but other people think that it exists. So I have to like conform this, whatever I'm doing, to like the idea of time. But time itself is just like, it's the passing of, like, as Nick said, of like heavenly bodies and all the way from like the subatomic all the way up. But it's only through human perception that we can even notice these things. So like without that perception, I think time doesn't exist. So it's almost like a measurement, and that's it. But all the pressures that we put on each other as humans because of time, I think is I think it's pretty BS. Like I can't stand time.
I see. From a social perspective, yes, it's something to grapple with, especially when like I have this Fitbit, and I guess you have to sync it on the regular or else it starts to display the wrong time. Maybe that's because it died and then I didn't charge it. But, there's all these little hiccups that show up in terms of our understanding of what the right time is. And now we have digital watches that can sync up to the Googleverse or whatnot. But before that, when we just had like the wind-up watches, it's a wonder that any of us had the same time, like.
Well, especially with mechanical watches, which notoriously lose or gain time.
Right. Exactly.
Mm.
And then, you have like, a wall clock or something, and like that could be fast. But if that's the boss's clock, then you're like, oh, that's the clock that matters. Um, yeah, and then even on like the larger scale, I think I start with this question because the Hubble constant, for those of you who don't know, it's really trying to describe how fast the universe is expanding at different distances from a particular point in space, with the goal of understanding how old our universe is. So in a lot of ways, that's kind of like measuring time. Now, before we get into more of that, it's kind of interesting to just think about like the history of time. So in ancient Egypt, they had sundials. That was about 1500 BC. And of course, even BC and AC, it's like, we have these measurements.
Mm.
So I don't know. It's just interesting how we've always kind of tried.
PC and AC is very weird.
It is,
Yeah.
right? Because like,
It's like we decided that, okay, this one guy that lived at the year 0, or no, he just lived, and then we're going to mark his birth as the year 0.
yeah.
Like different religions have different calendars too that are off by like thousands of years.
Yeah, I think the
So,
Totally.
Ethiopian calendar is like in the 1500s right now or something like that.
so it's like how like this measurement just kind of seems as just a something we do out of convenience.
Mhm.
So we have some like bearing in the world, I guess.
It's
Mhm.
funny, even though the like you're saying that you think calendars are off, but they still acknowledge that there was a 0 point, because the Earth isn't 1500 years old. The Ethiopian calendar, it's the year 1500. So at some point they said that there was a 0 point, and I think that that's strange to me.
Yeah.
No,
Go
for it,
ahead.
Dale.
Just gonna say, even with the Hubble constant, the idea that the Big Bang is this 0 point, you're like, okay, I guess. You're trying to,
Even before that.
Yeah.
right.
Even like our like leap day, right? Like we're so
Yeah.
good at time that we have to add an extra day every 4 years just to make sure we're still on it.
Yeah,
Yeah,
just to
it's very
correct.
strange.
Right, which you think like, why don't we just? Well, I guess you can't make certain days longer. I don't know. I mean, like, yeah, why did everything work out perfectly except for that 1/4 of a day each year? Like,
And then if you take the point of observation of like any particle, like you and I can observe the same thing, but it might be at 2 different places.
yeah.
So if you're trying to like measure how far something moves over some time t, then you can get all strange in it.
Oh yeah, and this is why I was like, I don't know if this show is going to be really it's just going to be really heady. Now just thinking more about time in terms of like its functioning, because okay, so like there was this endpoint, right? So Egyptians, they invented the sundial. I don't know if they did that for the express purpose of like, we're gonna have a meeting, John, at 1 o'clock, or what exactly the reasoning was, if it was to track aging and their empire and stuff like that. But like, to live in a world without time, do you think that it's a good thing that we invented time, or do you think that like we could go back to a time where there's no time?
It would seem to me that the sundial is like the most useless of the time telling tools, because like, especially in like an ancient Egyptian setting, just go outside. Just go outside and look where the sun is, and you'll find out. You don't need to go to a sundial to figure out what the time is.
But it is also really hard to be like, hey, let's meet up when the sun is 27 degrees or pi/4 in the sky or something. It's also very difficult to do. So I can see where time can be at least a little bit useful.
I guess. Nah.
Just a little bit. Well, okay, so we have some advocates for usefulness of time. Now what about time as it relates to our universe and its aging? Why should we care how old the universe is?
Yeah, it seems kind of arbitrary after you get past billions of years, It's like, Okay, cool. So
Wait a minute. You're telling me you can't mentalize billions of years of
yeah,
time?
right, exactly. Yeah, can we film it? No. Okay, well then I guess I just have to believe you that it happened.
Right.
That's
And
one
it's
of those
even
things.
like billions of years BC, right? I mean, or is it
Yeah.
I don't know whose year are they
It
talking
doesn't
about?
matter at that point. The weird, time thing that we have is literally like a sliver of the pie chart. But
It's true.
yeah, it's just bizarre because it gets very arbitrary, especially once you expand it outward towards the universe. It's like, okay, well, we know that the Earth is around 4 billion years old, and the universe is around 14 billion years old. What in the heck was going on for 14 billion years? Just gases forming. Like, do we really need to include that part?
I mean, yeah, it's kind of important if you enjoy gases
No, I'm
forming.
just I'm being a little hyperbolic for sure.
No, no, no,
Yeah.
I got you.
I love it.
But there's like, I mean, what else are people doing with their lives, right? They have to think about this stuff sometimes.
It's so strange. We started off. It's like basically the universe is just hydrogen gas becoming sentient and thinking about itself. That's all it is. Like wondering where it came from.
And then
Oh,
when we
wow.
build AI, the AI is going to do the same thing, just for way longer.
Exactly. Oh yeah, absolutely.
Though it might be observing a different gas.
True.
Sorry, I just think like imagine like the human scientist farts in front of the AI as it awakens, and its like first job is to figure out what this gas is. Anyway,
That's a Futurama episode or what?
potty humor. I'm sorry, I'm a fan. Well, okay. Thank you. Okay, so let me get into just a quick little 2-paragraph. So I was reading about the Hubble constant, and it is a rabbit hole because it's hotly debated, and this is part of why I ask why we should care, because the aging of the universe has undergone a really, really long revision. That is to say that when we first started talking about it, and I'm just scrolling down, so Edwin Hubble, when he first came up with the constant, and the way that he got to that, he clocked the age of the universe at about 2 billion years. And then Walter Bade came in.
Well, what a nerd.
Yeah.
He was way off.
He was way off, yeah. And I forget the reasons between these different folks. And they have to do with like, again, the way they measure it. So I'll circle back. But you had Hubble clocking it at 2 billion years. You have Bade clocking it at 3.6 billion years. Sandage says it's 5.5 billion. Then he learns some stuff and then he revises calculations. He's like, no, it's between 7 and 13 billion years. Then there was this brief moment where we got caught up in global or globular clusters or something. And then we thought it was 15 billion years old, but then we came back to about 13.8, which is where we're at now. And you'll see people now who've dedicated their life's work to perfecting that number. Is it 13.8 billion? Is it 13.789276 billion? Like just getting it really, really, really precise. And so just to go back into this article, it had this really cool intro that said, from the moment the universe burst into existence more than 13 billion years ago, it has been expanding, with galaxies visibly flying apart from each other. And to make sense of the physical laws governing the cosmos, astronomers have tried to measure one of the most important numbers in cosmology, the Hubble Constant, which describes how quickly this expansion is happening and the universe's age in turn. But recently, multiple efforts to find a value for the Hubble Constant have turned up a potential crisis in cosmology. The universe seems to be flying apart faster than expected, and if confirmed, this baffling change would force astrophysicists to rethink the fundamentals of our universe, which currently don't provide for such a change even after accounting for dark energy, a mysterious force driving an acceleration in the universe's expansion. So just right there, do you guys have any questions or
Well, yeah,
thoughts?
obviously. Uh, I don't know. I
Well,
just kind of got this idea of like the universe being a firework that's exploding in slow motion, and it made me wonder, like, if the edges of the universe are moving faster than what we kind of perceive, does that mean that we're in a part of the universe that, like, our time grid is different than another part of the universe? Does that make sense? Like, are
Yeah.
we does time move faster on the edges of the universe?
hmm Yeah, I think that's a lot of where they're trying to narrow this down. So for these show notes, I have like 20 pages that are scrapped. And in some of them, you had people who were testing the constant that we have now against blind studies of new observational methods that will take into account like dark matter, for example, which could say that we have more dark energy going on and more gravitational pull that's skewing our perception of time and the velocity of galaxies near us, at least from what I can understand. Which doesn't seem satisfying because again, then you're like, well, what's dark energy?
how do you start to see something that's not really seen, like antimatter and all those
Yeah.
fun things?
All those fun things. Yeah. What about you, Mike? Any thoughts just on that little discussion?
I mean, like, I can see time working as a wave, like if you're being pushed off by that dark energy force, then I can see where time could be moving faster, right? I guess
Hmm.
depending on which planet you're on, time may feel different as well, and where you're
Yeah.
at in the multiverse, even.
Oh gosh. Yeah.
That
Yeah.
reminds me of the movie Lost in Space. Do you guys remember that one? The
The
one
one
that
you
happened
brought up the last time we talked about space. You love it.
with Matt LeBlanc? Yeah,
Oh.
Matt
Oh
LeBlanc.
yes, that one.
Yeah,
Yeah. Hmm.
Joey's in it. But yeah, they have this part where they come across this ship that's been like orbiting this super massive planet, and it's like the time differential is way off. Like they're in the future for some reason because of the
Mm.
gravitational pull. It's really, really,
Ooh.
really kind of cool. Yeah.
Ooh, I like that. Yeah. And I think that really makes these articles hard to sift through because it's almost as if every single line where they talk about some variable or some inconsistency or an anomaly or a course correction, it gives you the opportunity to spin out into all these other ideas and
Well, yeah. And
conclusions.
it makes you wonder too, why are super dense celestial bodies manipulating the fabric of time? Why does that happen?
Yeah.
It's tied in with space, though, right?
I suppose, but it's still kind of odd because we're talking about it being a construct, but then if that were the case, it's more than a construct. It's like a mathematical inevitability or something, or some sort of architectural matrix.
Hmm. Well,
Based
yeah.
off of human perception, though.
I
Yeah.
suppose. But what if you
Well,
could get
and
a
like this is
machine to perceive those differences?
well, you'd have to
Uh,
chuck it in different places of the universe
Yeah,
for sure.
yeah, of course.
There's like a computer cycle, or a computer cycle. A computer would sees time differently. Like the cycle of it, like the pulse of energy is like 10 to the negative 9th to 10 to the negative 12th. So that would be it's like quote unquote second. And like even with flies, right? They see time differently. There's a whole thing about time dilation. So like on the
Mhm.
edges of the universe, right? And I suppose I say time is moving faster. It's the dilation. It's the feel of time. You can also do this mentally with learning. As you accelerate learning in theory, what you're doing is you're changing like your feel of time and dilate the dilation of picking up the act of picking up a new skill or idea shortens and your experience of time changes. If
Mhm.
that makes sense.
No,
Yeah,
I'm not
yeah.
I don't know. You mean like when you really get an idea, you're like, "Oh, this is a great idea," and time goes faster?
No, like
I don't think
as
that's
you
right.
as you start to pick up as you start to learn how to learn, um, the 8 hours to learn uh, a however much you can read of a textbook and do the problems in that time changes. So as your first attempt, you may only get through 20 pages, but your second attempt, you may get through 21 pages. And as you keep incrementally, you'll get through more and more pages within the same amount of time. So the dilation, that feel of time, changes. And near the edges of the universe, I can see where that edge is being, like that feel is being pushed off by like dark energy and things like that.
Oh, totally. And I think that like the feeling of time is something that I definitely want to do a longer episode just on time. Because, you know, we're all in quarantine and I started to wonder like if we had no calendars and no clocks and we didn't really have a way to measure this duration, like would it still feel the same, or is it the noticing of the time making it feel longer? And so like I guess I think it's a really cool concept to ponder. But to get into just go ahead, Nick.
Oh no, I was just gonna say I think that the issue is that celestial bodies are the clocks for us, you know. So you'd have to be put in some sort of vacuum where you have no external output, you know, or input. Because you know we have our sun and our moon that lets us know time, you know, stars tell us time and seasons. So I mean, yeah, you'd have to be in some sort of vacuum to not really experience it, I guess.
Or on an Earth with like 3 moons and 2 suns, so you don't, it's kind of fuzzy.
Or a mental asylum.
Yeah.
Or that. Yeah. Oh gosh. Well, to just get into the Hubble constant and how it's kind of how people got to the point of saying this is how we're going to do things. Now, I think it's interesting to just look at this history, and I like that you mentioned celestial bodies, Nick, because throughout time, humans have noticed the stars. And, you know, you don't have a lot of distractions, so soon you notice star patterns, you notice constellations. In 1608 is when we developed the first telescope. And it was in the early 20th century that we began to notice faint and fuzzy patches of light in the sky. These were once called spiral nebulae, and Immanuel Kant actually called them little island universes, but now we just refer to them as distant galaxies. And for all of this Hubble talk, these galaxies are what give us a point of reference. They're at the heart of this equation. And so the Hubble constant, again, it's a unit that describes how fast the universe is expanding at different distances from a particular point in space. It's also known as the constant of proportionality in the relation between the velocities of remote galaxies and their distances. And it expresses the rate at which our universe is expanding. And to the point of why we should care, the Hubble constant is actually one of the most important numbers in cosmology because it's needed to estimate the size and the age of the universe. It also helps us understand when we might collide with other galaxies because, as you know, the universe is expanding, we're hurtling towards things and things are hurtling towards us or away. So it'd be kind of good to know when that's all going to happen. And so in clocking the universe, this is where it gets really interesting. So the value number, it's estimated by measuring the redshift of distant galaxies and then determining the distances to them by some other method than Hubble's law. And this approach forms part of the cosmic distance ladder for measuring distances to extragalactic objects. But what does that mean? So I had to kind of watch a couple of videos and images to kind of get through this. So if you guys have questions, by all means, interrupt me. It starts out with 2 kinds of data. So one is how far away a given star is. And so to measure that distance, astronomers use a variety of tools from geometry to careful observations of stars called Cephoid variables. And then, so these stars, they brighten and dim regularly. There's like this pulsing that happens, and the rate of the pulses is closely related to the star's overall brightness. And the brighter the star, the more slowly it pulsates. And they also look at how quickly these stars are moving away from us. And to measure a star's relative velocity, astronomers look for shifts in the star's emitted light. So basically what you're trying, you know these stars are pulsing because stuff gets in the way or they're rotating in weird directions. So they get bright and then not that bright, bright, not that bright. So they kind of try to average out like what the top brightness is. And then they start to see, okay, so now we know how bright it's been for this long. It's starting to dim. So we know it's moving away. Let's start to measure that from the time that we started observing it, essentially. And so by measuring a Cephoid's pulse rate, astronomers can work out how luminous the star is by comparing the absolute brightness with the one we see. We can infer how far away the star is from us, and combined with other observations of certain kinds of stellar explosions to measure distances deeper and deeper into the cosmos. So do you guys follow that a little bit? I have some other
Yeah,
points of reference.
I'm slightly familiar with the redshift sort of tool that they use in order to measure that stuff. Yeah.
Oh, cool. Okay. And I thought it was really interesting that in a lot of ways they kind of rewind to the Big Bang and they just assume like, okay, so that's when all these galaxies were right on top of us. And then you fast forward to the now and you can measure how far away they are. So some galaxies are further away from us than other galaxies, and they can start to say, okay, well, is this one moving faster than this one? Or like how did those distances happen?
Mm.
And so you have like Earth, let's say you have galaxy 1, that's like 10 minutes away. Galaxy 2 is like 20, like also 10 minutes away because the clock is the same for every object. But so if galaxy 2 is super far away at this point, you have to assume there's some sort of velocity shift going on. And so this is how they start calculating things, is they have their assumed constants and then their observational data, and they just kind of blend it all together, which I thought is really cool. I already can feel like there's opportunity for error, and I think this is why you've seen so many shifts in the way that they aged it. But just having said that, any questions or thoughts?
I feel like I need a degree to have a question about that, to be honest.
Whoa. 1 second.
It's weird.
Oh, I guess she has a question.
Yeah. Oh, I don't know. I mean, it's incredible to me how we've even put those things together. Like,
Oh, I agree. I totally
Yeah.
agree. It's so intense. And I think that like one of the cool things that started to happen with this, like when they were going from 2 billion to 3.6 to 5.5, one of the points of comparison they used were looking at the oldest rocks on our planet. So, when Hubble was like, it's 2 billion years old, well, there's asteroids that have been dated to 4.6 billion years. So that can't be right. And so it's like just chipping away at like what could be changing this number.
Yeah, it's continually finding older and older things.
Mm-hmm.
That was so sorry for the interruption. My phone just decided to play YouTube. That's
Nice.
cool.
Nice.
Yeah, it's completely locked and everything. It's like there's like a root. Someone rooted it or something. No.
Oh.
Yeah, it's interesting how they use galaxies as like quanta for measurement.
Mm-hmm.
But I wonder if it like if they're using the same clock for all of them, aren't galaxies forming at different rates though, at different times?
Yeah. Yeah. And they move in different directions too. They don't just go in one direction, because you have to think about it. Like this is also assuming like the Earth is the center of the universe, which it's not. So if we observe something moving away from us, we think it's moving away from us like at a 90-degree angle, essentially. But it's not. It could just be moving on its own path perpendicular to our planet. And so the moment we start observing it, we're like, oh, 90 degrees. And then, 10 years later, you're like, it's gotten dimmer, but it's in the same spot. You would think it'd be this way. And it's because it's got its own path. And so that's actually one anomaly thing that they have to take into account. Peculiar velocities, I think, is what they call it.
Now, some of these
Which
galaxies
also
don't
has
even.
to do with
Okay. What?
what? Oh, just to wrap up, peculiar velocities also refers to those that are tugged by the gravitational field of nearby galaxies and clusters. So there's
Yep.
that whole thing to contend with too.
Because you're gonna have a bunch of weak forces interacting on it, pulling it in different directions.
Yeah. Even our galaxy is probably getting pulled somewhere in some weird direction by like the Andromeda galaxy or something else.
Yeah.
Wait, are we in Andromeda? Or is that our
Yes.
neighboring one?
We're in the Milky Way.
We're in the Milky Way. Okay.
Mhm.
Celestial influence.
Yeah, more celestial influence.
I just got a
Um,
picture of like a badass galaxy with like, tattoos and like smoking a cigarette.
That's a
Celestial
cool galaxy.
influences.
I want to go hang out with that. What?
Sorry. You were gonna say, Nick.
Are you sure I can say it now?
Yeah.
All right, cool. No, I was thinking because okay, so are some of these galaxies no longer around that we're seeing?
Yeah, we could just be seeing like the death light of some of these in theory, right?
Look at Orion's leg, left leg, left. One of Orion's like stars has already died. And the light that you see, it's the one that pulsates and looks slightly reddish. The
Dang.
pulsates more, I guess. But those are the death light, the pretty death lights of that poor star. And
Yeah.
like the thing that's gonna bum me out is that one day you won't be able to see that. Like we've lost a
Yeah.
constellation in theory.
Yeah, how many constellations have we lost in human history? I'm sure at least a handful.
That's super sad.
Mm-hmm. Yeah.
Well, and then it's
it's bizarre.
interesting. It is. And like it's interesting because they were talking about the BeetleJuice star, which is like one of the brightest in the sky. And they thought that that also was going to die because it was dimming back in like 2019. But apparently in 2020, one of our great discoveries is that it was actually just a star burp. Apparently it just released a bunch of, let's see here. It says the Hubble Space Telescope revealed that the star likely sent out a super hot jet of plasma that cooled as it whipped outward. And the process formed a cloud of stardust that could have blocked Betelgeuse's light from eager earthbound viewers. And then the star returned to its normal brightness this past spring.
Mm.
So it's not dying.
Vomited.
It
had
burped.
a rough night out. Had some alcohols. Mixed the dark and clear, and then it got all hazy from there. And released a bunch of
Celestial
plasma.
influence.
Yeah.
It's true. No, and you're totally right, Nick. I mean, like, this is where it just seems so impossible to try to nail any of this down, but it's also really impressive what we have figured out in the process of trying to figure it out. So we talked about peculiar velocities. There was another thing about expansion rate changes. So that was just the idea that, we think everything's moving at this constant velocity, but when you look at the observations between this one scientist doing the measurements and this other one doing the measurements, they started to notice that there were changes. And so one of the things they realized is, so remember when I was talking about the pulsing and how they try to find out when it's most bright so they can start to pinpoint like the movement and the dimming of the brightest level of it.
Mm-hmm.
Okay. So they come to find that there's actually two different types of, what are they called? Cephoids. There's like a bright Cephoid and like a mini bright Cephoid. And so before we were lumping them all together. And so, again, if you're taking this aggregate data to get the age of the universe, but you have two different sets of data type, they had to start to go back and re-identify, okay, well, this one's Cephoid A and this one's Cephoid B, and then recalculate everything and revise their number. So that I thought was really cool because it's like, okay, so if you have galaxies with lights that are brighter than others, like what could be causing that?
Bigger stars?
Maybe, More gas? I don't know.
No, it's just bigger stars.
Cosmic influences.
Yeah, cosmic bodies.
Cosmic
Yeah.
bodies.
No, I mean, I would just assume that a brighter galaxy, would have just more stars or just more large stars,
Or maybe younger.
younger stars. Yeah.
Mm-hmm.
Yeah, because it sounds like, yeah, from these different observations, there's like a latent space that can be found with that kind of like helps merge these two numbers or these different measurements and observations into one like cohesive matrix.
Yeah. Or, maybe we are starting to see categorizations of galaxies. I mean, think about it. There's no way these galaxies are all the same. And if part of the goal of measuring the age of the universe is to help wrap our minds around the rules of the universe, then it helps to start categorizing it. The rules in a Cephoid galaxy with a Cephoid period luminosity relation of X might be completely different from that with the Cephoid period luminosity relation of Y. And I'm probably even misinterpreting that. But if you want to look it up, that's the term. And it's kind of just cool, you can just do a whole deep dive on just that. But there's more. Apparently, the average of the stars in the galaxy is also something of note. So again, they were noticing that within each of these galaxies, you do have stars that are brighter than other stars just naturally. Like Nick said, maybe because of size, maybe it's their proximity to us, or like Mike said, maybe it's their age. So the other thing to keep in mind is it's not precise because they're still having to average out the data. Now, let's get back onto cosmic microwaves. Do you guys know much about the cosmic microwave background of the universe?
That noise is pretty gnarly to listen to.
It's everywhere, too. You can point a satellite in any direction, and this empty universe is abounding with sound. And
Just
it's
turn
like,
your TV
where is it
to
coming
channel
from?
1.
Yes. Yes, it's the same thing.
My childhood.
Yeah. Exactly. Well, yeah, it's just pretty crazy. And let's see. There's a Swiss-based effort to look for and monitor gravitational lenses. So, this is where I kind of got a little bit lost because they were talking about what is it? This background resonance cosmic microwave background noise. Somehow they're able to ping off of that, and then there's this thing called gravitational lenses. So these are regions of space that contain a lot of mass, and then they warp space-time itself enough to bend any light that passes through it. So this is an added layer of confusion because now we have things bending stuff. So you're trying to observe stuff. They're finding ways to go around certain things to get a more accurate assessment of the brightness of the light. At least that's what it sounded like to me. And so just to read off, so this one, it's called Cosmo Grail, and this is the one that's a Swiss team. They wrote that a gravitational lens happens to fall directly between us and a faraway object, bending its light so much that we see several images of the object cloned around the lens's edge. These images are not synchronized in time, and one image's light may have been bent less, giving it a straighter, quicker shot through the lens, whereas another image's light may have been delayed by passing through especially warped space-time. They also these gravitational lenses are backlit by quasars. So these are extremely bright objects powered by supermassive black holes. Crucially, the lensed images of the quasar will flicker just like the quasar, but not all at the same time. And these tiny delays depend on the distribution of mass within the lens and the distances between us, the quasar, and the lens. So if researchers can figure out the mass needed to get the observed lensing, they can combine it with the time delays to estimate the Hubble constant. So this is where I'm saying the more recent research is super intense and awesome. So this last little bit says, if the matter at the heart of a gravitational lens is a galaxy, researchers can measure how quickly that galaxy's stars are rotating and then combine this data with the time delays to figure out how wide the galaxy must be. By comparing its true diameter to its apparent size on the sky, researchers can then pinpoint the lensing galaxy's distance from us.
It's pretty cool.
Like, yeah,
just-
that's really cool.
Photons are such delicate little things. Jeez.
Oh my gosh. Yeah. And I mean, like, I don't even understand that. I'm going to have to deep dive more into quasars and how supermassive black holes can power these bright objects. And then just look at, like, they're trying to measure how wide the galaxy must be. That's astounding. I mean, because we just think it's infinite, but is it? I mean, it can't be finite. But can it? It can't be infinite. It can't be
No, you're
both.
thinking of
Is
the
the weird
universe.
thing.
You're thinking of the universe.
Oh, I am. But I mean,
Mhm.
like, when you start amassing all these galaxies, like, it just, if you can measure one thing and you get a constant that's like way over there, you can start to ping that information off of other stuff too. So it's like all this stuff builds on itself. So I think it's just pretty cool.
Yeah, ad infinitum though. I mean, like,
Yeah.
that's kind of the issue. Is like, yeah, you might find trends, but if you're looking at an infinite data set, then it's just going to be an infinite amount of trends.
State
Yeah,
space
yeah.
searches. So, like, yeah, you're gonna have to find good search algorithms to look through this stuff. But like infinite spaces when it comes to like AI and things like that, that's pretty much its home. It's where it
Right.
where it where it lives. Like when I was talking about latent spaces, it's, I guess like a technical term in linear algebra, but I'm talking about the basis space for all galaxies, and then you can start to search through there. And with the Hubble constant, I imagine would be some part of that. But you can do a lot of cool stuff once it starts to work in. But you definitely have to make your infinite set discrete, or at least focus on discrete sets within whatever infinite set you're working in. Does that make sense?
Right. Yes. You have to really narrow down the micro in order to accurately depict the macro, because you could be off by like a huge margin once you apply it that way.
But even as you cut through the macro, each step in the micro that builds on top of each other is hopefully gives you an accurate description of the macro. But if you move from micro to micro in the wrong way, then you will get like the wrong idea. You'll end up in subspaces you don't want to be in.
Oh yeah. Well, and this is how like I wonder about people who work at like JPL and NASA and stuff, because for sure they're hoping you can start to measure a galaxy, because then you know exactly how much propulsion you need to get somewhere. You know exactly how much energy you need to power some robot to send samples back from like the farthest ends of your galaxy. Like you can start to build benchmarks to aspire to. And I just think it's just amazing that we can calculate things to such precision. Even like what you're saying, like all those things that they account for, it's just really inspiring what humans can do.
And this all starts from the idea that the galaxy is somewhere between 7 billion to 15 billion years old or something like that. That giant range, right? And then you just slowly break down your subranges until you find something that works well with your observed reality.
Right. And then like what I thought was kind of interesting in this particular instance with the what is it, the gravitational lenses, is that you can make really, really close approximations about distance and things like that, but there are more methods coming online. So these are like more ways to ping information or bend this or observe that. And in the future, detections of ripples in space-time called gravitational waves flung from collisions of neutron stars could provide another type of estimate. And they're doing all these blind studies because they're trying to make sure that like this is still within the range that their findings about probably true. But what she said is that the main question is if our cosmological model is in danger. She says, I don't know the answer to this question, but I can say that we are getting to the point that we have to consider this option really seriously. So this is the idea that as our ability to observe gets better and better and measure and all that stuff, we might see some major revisions of cosmological models in the future.
Yeah, it's pretty cool. I mean, back propagation's a thing. Or
Yeah.
backtracking. But if we got some, that's the point of science, is to get yourself wrong, right?
Mm-hmm. I think
And
so.
in the search of bigger truth.
Yeah, exactly. And that's the end. That's all I got for today. I really wanted to share some of the cool new observational techniques and just marvel at how amazing and awesome humans are. And just start looking up these articles because I swear stuff is coming out every month, and it's just so cool to think about it.
Indeed.
Awesome. All right. Well, thank you, ladies and gentlemen, for giving us a listen. We hope you enjoyed this episode. Special thank you to Ayla. Thank you for bringing this episode together. And I'm sure we'll have a conversation about time at some point as well. There's never a shortage of topics that we can go after.
Yeah.
So, yeah, but thanks for taking this ride with us, everybody. We really appreciate you. If you have any input for us, please feel free to leave a comment to any feedback that you might have. If you have any ideas about episodes you might like to hear us talk about, that would be wonderful. Otherwise, just enjoy, and thank you once again. And until next time, Cognonauts, we will see you on the next Exofathom. Good night.
Peace.
Later.